great pleasure to introduce the next speaker today, Professor Eli Yablonovitch from the University of California, Berkeley. The title of his talk is Optical Antennas, Spontaneous Emission Faster than Stimulated Emission.
Right, I'll be speaking right into the microphone. And before I get started, I want to advertise a small talk I will give tomorrow on photovoltaics. And this is kind of an example, if you can see, I'm not sure you can see it from the back, but it's basically a little flexible thin film gallium arsenide driving some blue LEDs. So it'll be an interesting example of some photovoltaics. But my topic today is actually on a different topic completely, and this has to do with the importance of antennas and how in physics we seem to have dropped the ball on antennas, and now it's coming back and we have to understand them better. Now, one of the things that antennas enable is that you can have spontaneous emission, you can revolutionize spontaneous emission, make it faster than stimulated emission, and that's kind of a revolutionary development. Now, the way to think about this is, let's say you had a quantum dot and it's trying to emit, and it's able to store the energy. Two requirements for spontaneous emission. You have to store the energy, and then you have to radiate the energy. And the problem is that a quantum dot is able to store the energy, but it is too small to be an efficient antenna. In fact, an efficient antenna should be of the order of half a wavelength. So for this reason, spontaneous emission has been penalized throughout history. However, if you provide an antenna to the quantum dot or to the molecule, suddenly you overcome that major second problem is that the molecules are too small to act as antennas. Now, to give you an idea how serious this problem is, let's say we had a very small dipole moment, which we have. This is a typical dipole moment in the 3-5 semiconductors, and so it's maybe 1,000 times smaller than the wavelength. And so what ends up happening is that the penalty in the spontaneous emission is 1,000 cubed. But to see that, you have to actually go through some antenna physics. So we'll get into that. So there's a tremendous opportunity then to completely change the photophysics. So spontaneous emission is actually the faster emission. Now, where are we today, though? Spontaneous emission is slow. You have LEDs that are used, for example, on television remote controls. They're not very fast. You don't need much data rate for that. But you're competing with lasers that are quite fast, but even the lasers saturate at 25 to 50 gigabits per second. So if you could somehow increase the rate of spontaneous emission by 200 times, the LEDs can compete with the semiconductor lasers. Now, the way to think about it is as follows, and that is that the laser it's regarded as fast, but you need a threshold current. So finally, you get the threshold. LED, maybe it's slow, but it starts right away, so you don't have to invest a lot of threshold current. Now, the laser can be very fast, but you have to drive it very hard. And traditionally, the LED, you don't have to drive it very hard, but the speed never speeds up beyond this low level, so it's rather slow. Now, the way to overcome that is to add an antenna to the LED, and so you have no threshold current for the antenna. The laser still suffers from threshold current, and the speed saturates, but the antenna LED can be faster than the laser, and 100 gigahertz and up is the potential speed. So this is a very attractive opportunity. So we have a vision that we will have short distance optical communication. We have now silicon photonics, but it is used to go off chip. To go on chip, you need something as simple as a wire, and you need a bulletproof device like an LED, which is far more reproducible than lasers. And so this is a worthwhile goal. Now, there has been a lot of work previously on antenna-enhanced light emission. It's becoming quite a big thing. Some nice work from Duke University on little silver cubes, and from many other sources. But almost all of these have been optically pumped. And so the question is, can we get interesting electrically pumped device? I'll show you, that's the culmination of the talk right now. Now, what is this idea of concentrating energy? We seem to think that this is a particular property of plasmonics, but actually it has always existed in terms of metals. And for example, the scanning tunneling microscope is operating at low frequencies, and yet it concentrates the electromagnetic energy to a small spot. And long ago, they gave the Nobel Prize for visualizing single atoms. But this idea of concentrating electromagnetic energy with metals, it's actually even older than that. Imagine taking two spheres, and you can concentrate the electromagnetic energy, again, in a very small spot between two spheres. And these spheres, if this is half a wavelength, this is actually a very good antenna. Well, where'd that come from? Actually, it came from Heinrich Hertz. If you go back and look at the really old stuff from 1888, he started out making spheres, and the spheres were very close together, and he would draw a little spark between the spheres. And of course, he could not go to the store to buy radio components. He had to make everything himself. And the transmitter was basically two spheres, and the receiver was also two spheres. This was the receiver is basically a little wire loop, and the spark would jump between the two spheres. However, I want to just point out that if you have such a loop with two spheres, it looks very much like an LC circuit. And in fact, every antenna is analogous to, every antenna actually is an LC circuit. So this goes back to 1888. Notice in 1888 there was no plasmonics back then. Now, if you want to learn about antennas, you have a problem. And so I learned from some very famous books. I learned a lot, but I didn't learn much about antennas. For example, Jackson's Electrodynamics was the standard book for many years. Unfortunately, it doesn't tell me too much about antennas. Then I said, well, I'll go to the Feynman Lectures. That has everything. Well, it's a fantastic set of books, but you can't learn very much about antennas. Likewise, Yari's books are excellent, but you still don't learn much about antennas. You'll learn in a minute why I happen to have stumbled across antennas. But I did publish a small tutorial, a 2-page tutorial. It was an experimental paper, but the first 2 pages are dedicated to a tutorial, what you should have learned. Now, what happened about 70 years ago, antennas dropped out of physics. And so there's a few basic things to learn. And one is the cross-section of the absorbing the antenna. Another is the radiation resistance. And the third is Wheeler's limit, which is extremely rarely covered, even in antenna books. So what is the cross-section of an antenna? It's lambda squared over 4 pi if it's isotropic, and if it's more directive than isotropic, you just adjust it according to the directivity. So this is a universal property. Of course, to me, an atom is also an antenna because it captures radiation from plane waves, and it gives you an idea that the cross-section for capturing energy in an atom is much larger than the size of the atom. Of course, this is true for this is a universal property. Notice I don't have to tell you anything about the antenna. It's a good antenna, bad antenna. It's a small cell phone. It's big. It doesn't matter. It's the same cross-section. It's important. Another important concept is antenna radiation resistance. This is covered in some books, but there's a neat way to derive it. In physics, you're taught that radiation comes only when you accelerate electrons. You can go from the acceleration, you can write that as frequency times velocity, and in the end, you end up deriving that radiation is coming from AC current, and it's proportional to the radiated power, it's proportional to current squared. So it looks like I squared R, and this thing in front is radiation resistance. And it gives you a very nice thing. Once you have radiation resistance and the capture cross-section, you can equalize, you can have an equilibrium between the captured power and the radiated power. And in this way, you can figure out, instead of being an optics person who talks only about watts per square centimeter, you can be a circuits person who asks, what is the RMS current, or what is the RMS voltage in your antenna structure? And both are equivalent and are connected by this equation, so that's kind of neat. And you can derive the optical voltage, RMS voltage as well. Now, the application of this frequently occurs in circuits, in a circuit model, and this is a circuit model. It's a very simple circuit model for a radiating antenna. Every antenna is an LC circuit. You have some radiation resistance, some ohmic resistance, and you might have a load that you're trying to deliver power to. The most confusing thing about this is you have to do this in MKS units. It's very hard to do this in CGS units because you need the impedance of free space, which is that other fundamental constant, 377 ohms. But it's very confusing in CGS units. It's 4 pi over c, so it looks like the reciprocal of the speed of light, but it's a good rationale for using MKS units. Now, this is the third important fact about antennas, has to do with the radiation Q. This one is very, very hard to find. This was published by a guy called Harold Wheeler. He was a very famous radio engineer in the first half of the 20th century, and he came up with this formula that said the difference between a good antenna and a bad antenna is a good antenna has a wide bandwidth, it has a low Q. So in antennas, everything's backwards. In optics, we often want a high Q, but in antennas, we want a low Q because we want energy to be radiated. And he connected, and then he said, if you have a bad antenna, then you suffer in bandwidth. The cross-section is the same. The cross-section is a universal number, but you suffer in bandwidth. And this is a severe problem. So in my class, I often ask the students, you see what ends up happening here, the size of the radiating object determines the radiation Q. So I ask the students, okay, what's your personal Q? But I'm not being fresh, it's a physics question. Okay, so how did I learn so much about antennas? So I started a company in 2000. I was overconfident. I had been to the best schools. I thought I understood antennas. It turns out I did not understand antennas, but it was very difficult to give the money back to the venture capitalists, and so they said continue on. So I had to learn, I had to study all these antenna books and figure a lot of this stuff out. The company eventually became successful, and its major customer is Samsung, and it has 3 factories around Seoul, so I'm actually very close to the factories, and it has shipped around 2 billion antennas. So it's, I would say the company is quite successful, but it forced me to learn about antennas. So what have I sort of derived is that antenna physics, it's what none of us ever learned, and we have to learn it now. It's not the same as plasmonics. It's not the same as the Purcell effect, and has nothing to do with the local density of states. It's just antenna physics. Now, let's think about what is the basic enhancement. So if you have an antenna and it sees a plane wave, so there's an electric field from one tip of the antenna to the other. Because of that electric field, you build up a voltage, and because of the antenna, that voltage drops across a very small space. So effectively, you're enhancing the electric field by the length of the antenna divided by that narrow space, and then for power, you square it. And so this is the basic enhancement factor. So it can be quite significant, especially if the gap is very, very narrow. Now, you could ask, how can spontaneous emission possibly be faster than stimulated emission? Here's the way to think about it, is that you have now this electric field from here to here, but it eventually gets concentrated into this narrow region in the middle, and you end up building a very big zero-point electric field. So there's a very old model for spontaneous emission. They say it's stimulated by the zero-point electric field. So in this way, we've taken the zero-point electric field, which was stretched from one tip of the antenna to the other, and we've concentrated it into a narrow region in the middle. And so in this way, we can build up the spontaneous emission rate. Now, if you did the same thing with stimulated emission, you'd get the same effect, but there's a problem. With stimulated emission, you have to have a pump field. So there's a pump field, and that pump field is not a zero-point field which cannot cause any damage or any nonlinear effects. That pump field has to be real, so you simply cannot build up such a strong pump field safely as you can a zero-point field. And for this, with this advantage, spontaneous emission can always be made faster than stimulated emission because you can have a bigger zero-point field than a bigger real field. And so that's how you beat spontaneous emission. Now, the way to understand this then is to put the antenna into the circuit model. I showed you an example before, but here's the only part that has quantum mechanics in it. And what happens is that in every excited state, let's say I have an excited state, there's actually little bits of current flowing back and forth in the excited state. That current can be written quantum mechanically in this way in terms of a matrix element, and then that drives the current of the antenna, and then you can insert this quantum mechanical current into classical antenna theory, and everything works. The only part that's quantum mechanical is the source of the current itself. The rest of it is just an antenna problem. Now, I promised you the equivalent circuit. It's a bit complicated. This is one example of an antenna with two arms. You have your quantum mechanical current is in the middle, like this, but you have to take into account all the different capacitors and inductors and resistors and so forth. And this is a reasonable model, a reasonable circuit model for the antenna. I should mention every metal object is an LC resonator, and every LC resonator is an antenna. So antennas are around us all the time. Now, here's one of the problems that comes up, is that let's say you have a dipole emitter, and the current is spread over a relatively large area if the dipole emitter is far away from the metal surface. But if the dipole emitter is very close to the metal surface, the current is not spread at all, and you get something that's known classically as spreading resistance. And the spreading resistance is bad because you end up having losses. Now your antenna is lossy, and your LED is inefficient, etc. So this spreading resistance is a very serious problem and prevents us from approaching metal surfaces too closely. Now, there are some resistances that appear in these problems. Obviously, I mentioned radiation resistance, ohmic resistance, but in addition, you have spreading resistance. And then you have extra spreading resistance when you allow for surface collisions. And when you allow for surface collisions, that's called anomalous skin effect. So it just means surface collisions, that's all. And then if you model a series of antennas, let's say you have a very good antenna and the efficiency is 75%, but then you start being more realistic. You put in a dipole source, you allow for the anomalous skin effect, and then you allow for this spreading resistance, and suddenly the 75% antenna is now a 35% antenna. So you've got to take all of these effects into account. Now, so what happens is that if you're too greedy and you want too much of an enhancement, you can keep getting the enhancement higher and higher, but unfortunately at around a 10 nanometer gap spacing between the antennas, all these resistances become overwhelming, and suddenly the efficiency drops even while the enhancement keeps going up. So it's very important to emphasize efficiency. So I'm going to show you now an electrically pumped antenna LED that we think could be competitive with lasers for short distance optical communication. The way to think of it, I said every type of metal is actually an antenna. I'm going to show you one type. Here it's a slot. So a slot is a perfectly good antenna, and the currents are flowing around this way, like this, and that's an inductor, and the slot is a capacitor, and so this is a little LC resonator. Now, this is a useful starting point for an antenna because what we can do is cover it up with metal surface. Now it emits only in the downward direction. So you'll see that this is very compatible with a semiconductor device, and it's a simple PN junction diode, and you can adjust where the quantum wells are. That determines the hotspot, basically. Obviously, you want to put the quantum wells near the hotspot of the antenna. So here is a cross-section of the device. This is what it looks like from above. From above, all you see is this silver bump. But what you have is a ridge of indium phosphide, and just think of it as a ridge going off like that. And the quantum wells of the light-emitting region is indium gallium arsenide phosphide, and this is your light-emitting region down here. And you do electrical contact to the silver antenna and electrical contact to the P indium phosphide, and now you have an electrically pumped optical antenna. Now, one of the nice things to do is a comparison with and without the antenna. It's very easy to do because you can put the active region, so there's the active region, you can put it at the sweet spot for the antenna, or you can drop it below. the sweet spot for the antenna. And then if it's below, down here, you don't get any benefit from the antenna. And so you can easily compare the performance with and without the antenna, and I'll show you some of those comparisons. Now, one of the things that happens is that you can detect, of course, as others have done, a tremendous polarization ratio, just a tremendous enhancement ratio. Now, I mentioned 200 times, and you're competitive with lasers. So there's polarization ratio. This is comparing the active region in the wrong place versus the active region in the right place, and just showing a very substantial enhancement factor of the order of 200 or so. And this is the same thing plotted as enhancement factor. So we're looking at enhancement factor 200 and above. Of course, others have seen this level of enhancement, and even they've seen up to 1,000 or more. But in this case, we're trying to keep the efficiency up. However, it's very difficult to maintain efficiency. Sure, the device is fast, but it is not yet efficient. This is some time-resolved measurement showing that the efficiency is dominated by non-radiative recombination at the edges, which is true for practically any diode device. So you have to fight the edge recombination. So the question rises, can radiative recombination ever exceed the non-radiative recombination at the edges? And so these are where the edges are, where you get into trouble. And so you have to do some things in the device design to assure that you're getting a good efficiency in the light emission. Now, one of the things you can do is to dope very heavily, and that's something that you would not ordinarily do in a laser or in an LED, but if you dope very heavily, you can increase the rate of spontaneous emission. So there's a few other tricks that are needed, and I know not everybody here is an expert at designing LEDs, but I'll just show you what the tricks are. So if you look at the spontaneous emission itself, that goes as e to the QV over KT. That's sort of fundamental. But the non-radiative current, it's seemingly very similar, but there's a very big difference. The diode quality factor is 2, so it's 2 KT. So if you pump very hard, the radiative part is always beating the non-radiative part. So that's one of the important things that you have to do, is to pump hard enough that you can overwhelm the diode quality factor to non-radiative current. And so the way to think about it, at low voltage, you're dominated by non-radiative current, and then you switch to the radiative part. And this is a universal thing. Everybody does this in designing light-emitting devices, or indeed for solar cells, you do very much the same thing. And as I mentioned, the other thing you have to do is p-type doping. You might be familiar with the BNP product, so you dope it very heavily to get a higher spontaneous emission, and you also benefit from the enhancement factor, which we're looking for at least a factor 200. And so with these two factors together, you make the spontaneous emission fast enough that it can compete with the non-radiative recombination. And so you can go through this and figure out the rate equations and all the different losses that occur due to non-radiative recombination. But at the end of the day, you can beat the non-radiative recombination. Now, if you want to know what in detail what is the mechanism, it's too much detail, but think of a ridge laser. So in a ridge laser, they don't bother to take care of the edges because they know the stimulated emission will compete with the edge recombination. So they have this ridge, and you have a successful ridge laser. And now, in the same way, instead of stimulated emission competing with non-radiative recombination, here we have an antenna-enhanced spontaneous emission competing with non-radiative recombination. And you can go quite fast. If you go down to a gap of 10 nanometers, you can be looking at 100 gigahertz speed or higher. But at the same time, you need to know your efficiency. So I think it's very important not just to mention enhancement, but also to go into detail in terms of efficiency. And here it is. It's the same mechanism that is used in ridge lasers, and we're looking at an efficiency of the order of 40–50%. So this is where this research is going, and we're actually looking toward taking this to a short distance optical communication system running at very high speed. So let me summarize then, is that we need this factor of 200 enhancement to compete with lasers. I think now a number of groups have demonstrated a speed up of spontaneous emission of 200 times or more, at which point it is faster than the laser. But now we have the prospect of electrical pumping with of the order of 50% efficiency. So I would conclude the talk by saying that the electrically pumped LED is now faster than the laser. So let me leave it at that and throw it open to questions. Thank you. So I wonder if I can ask a question to the audience. Have I made you angry by saying that antennas are not plasmonics? You could have a plasmonic effect, but antenna physics has its own beauty and something worth learning.
Okay, great, thanks. Hold on. Here, one question.
Eli, I have two questions. The first one, you started your talk by saying, you know, the laser has a threshold, the LED doesn't have, and but the laser is faster. But can't we put the two things together? And now it's more and more easy to get thresholdless laser with a very high beta, basically, where all the radiation goes in a single mode. So isn't that an equivalent winner? I have to ask you that question.
Yeah, no, it's a very good question, and it has to do with the convergence. So I think you're right. We're seeing a convergence between the LED and the laser. But I think the distinction with a thresholdless laser is that you tend to have a dielectric cavity for thresholdless lasers, and I prefer an antenna cavity or an antenna. Why? Because the antenna is designed to radiate energy away, not to keep it inside, but to send it out. But your point is well taken.
The next, if I may, short question is this. When you presented these ideas to make your LED buried and so forth, are you considering, because for example in the group of Professor Samuelson in Lund and some of the startup companies have made very high quality arrays of light emitting diodes, nanowire arrays.
Yes.
And it seemed to me that that's the ideal way to go.
Well, it's quite good. It's good to have nanowires. It's similar to the structure that I showed you, which is a nano ridge. One of the reasons we prefer the nano ridge is for optical communication, you still need a reasonable amount of power. And so what the ridge does, it makes the antenna active volume large enough to give you enough photons to do optical communication.
Any more questions? Okay, there. It's easier to go here than to go there.
Thanks for the great talk, Eli. So one of the other advantages of a laser is that the emission from the cavity can be made directional. And in principle, you have the dielectrics there to reshape it in a directional way. In the plasmonic device, presumably it's going to be like fairly non-directional. I'm wondering how you could shape the grating or something like this surrounding the active region to get a directional emission. And how much additional loss that might bring in.
So first of all, I object to calling this a plasmonic device, as you know. Okay. Now, however, in antennas, we have many tricks. For example, we have Yagi antennas, and so we put additional elements. And this was actually done by my collaborator, Professor Ming Wu, and he showed 70% efficiency if you add the Yagi elements, 70% efficiency into the single mode of the silicon waveguide.
All right, thanks.
Oh, go ahead.
Yes, Eli. I'm wondering why would you want to make the LDOS people angry, or do you?
Okay. Well, if you do local density of optical states, if you do it very carefully, you'll get the correct answer. But would you go to an antenna engineer? Let's say, for example, in my company is is selling a lot of antennas to Samsung, do you want to go there and congratulate them on the ingenious use of local density of states in the latest Samsung phone? So, of course, they don't use it. They follow the normal antenna theory. And the normal antenna theory, it may seem a little complicated, but it's very easily captured by the equivalent circuit. I don't need a local density of optical states. I'm a simple person. I'm an experimentalist. I'd rather have an equivalent circuit.
Okay, one more question here.
Can we consider an antenna as a low-quality cavity coupled with emitters, or it's something different?
Yes. Yeah, that's a good question. Is an antenna a local cavity? And indeed, when I'm teaching the senior level electromagnetics course at Berkeley, and I start the course on the first day, I say every piece of metal is an LC resonator. In other words, it is a cavity. Every piece of metal, literally, imagine a paper clip, and the metal is twisted around, and it's like a little inductor. And so every piece of metal is an LC resonator, therefore it's already a cavity. And every LC resonator, I say, is also an antenna because you have AC currents, and AC currents automatically radiate. So that's the way I prefer to think about it.
Well, I thank the speaker for a very nice talk.